Today we'll study sequence and series, and this first question is, let A1, A2 up to AN plus 1 be an AP and let its common difference be D. Now it is defined S1 as sum of the series from A1 to AN, S2 is from AN plus 1 to A2N, S3 is from A2N plus 1 to A3N. So each of the series contains n terms, and S1 is sum of first n terms, S2 is sum of next n terms, S3 is sum of again next n terms. Now it says prove that the sequence S1, S2, S3, it is an AP whose common difference is n square times the common difference of given progression. Now for this, what we'll do is we'll write this general series Sk, and we need to find the first of the series. Now if it is S1, last term is An. For S2, it is A2N. For S3, it is A3N. So for Sk minus 1, its last term will be A K minus 1N. Now here, its first term will be A K minus 1N plus 1. And then we'll have N terms. And its last term will be A Kn. Now this is sum of n terms of an AP. So its sum will be n by 2, 2a, and a here is a, k minus 1n plus 1 plus n minus 1 into d, and then we can write sk plus 1. Now here first term will be a kn plus 1. I'll go all the way up to a k plus 1n, and this sum will be n by 2, 2 a kn plus 1 plus n minus 1 into d. Now if the sequence it is an AP, then difference between any two successive terms must be independent of k. So what we'll do is we'll find sk plus 1 minus sk, and here n minus 1d will cancel. So we can write this as n by 2, and this is 2a kn plus 1 minus 2a k minus 1n plus 1. Now this 2 and 2 will also cancel. So this is n. Now this is kn plus 1th term. So it will be this a1 plus kn into d, and this is minus, and this is a1 plus k minus 1n into d. Now this a1 and a1 will cancel, and this k and d will also cancel. So this value will be equal to n square d, which is independent of k. Now since it is independent of k, it means this sequence, it is an AP, and this common difference, it is equal to n square into d, where d is the common difference of the given progression, and which is what we need to prove in this question. Now here the question is, let a1, a2, a3, an be an AP, then we need to prove that 1 upon a1 an plus 1 upon a2 an minus 1 plus 1 upon a3 an minus 2 up to 1 upon an a1 is equal to this right hand side. Now we have this one interesting property in arithmetic progression, and the property is arithmetic mean of terms which are equidistant from beginning and the end are equal. So that means a1 plus an by 2, it is equal to a2 plus an minus 1 by 2, it is equal to a3 plus an minus 2 by 2, and it will continue like this. Now we can cancel this 2 also, so we can say some of these numbers, they'll be equal. Now we'll take this series, which is 1 upon a1 an plus 1 upon a2 an minus 1, 1 upon a3 an minus 2 up to 1 upon an a1, and what we'll do is we'll multiply and divide everything with a1 plus an. So we'll write 1 upon a1 plus an, and we'll multiply everything with it. So it is a1 plus an upon a1 an plus a1 plus an upon a2 an minus 1, a1 plus an upon a3 an minus 2, all the way up to a1 plus an upon an a1. Now we can write this as 1 upon a1 plus an, and this is a1 plus an upon a1 an. Now we know that a1 plus an is also equal to a2 plus an minus 1. So we'll replace it here. So we'll write a2 plus an minus 1 upon a2 an minus 1. In the same way, a1 plus an is also equal to a3 plus an minus 2. So it will be a3 plus an minus 2. And this is a3 an minus 2. I'll continue up to a1 plus an upon an a1. Now what we'll do is we'll split these terms. So we can write 1 upon a1 plus an, and here it will be 1 upon an plus 1 upon a1, and here will be 1 upon an minus 1 plus 1 upon a2, 1 upon an minus 2 plus 1 upon a3. I will continue up to 1 upon an plus 1 upon a1. So here we have this series 1 upon a1 plus 1 upon a2 plus 1 upon a3 up to 1 upon an, and again we'll have the series a1 a2 up to an minus 2 an minus 1 an. So we have the series twice, so we can actually write this as 1 upon a1 plus an, and it will be 2 times 1 upon a1 plus 1 upon a2 up to 1 upon an. So this is equal to 2 upon a1 plus an into 1 upon a1 plus 1 upon a2 up to 1 upon an, which is what we need to prove in this question. Now the second question is, show that in an AP, this value it is equal to right hand side. Now we have this AP, A1, A2, A3, and let its common difference be D. Now we are given the series as A1 square minus A2 square plus A3 square minus A4 square, and it goes all the way up to A2k minus 1 square minus A2k square. Now what we'll do is we'll pair these terms taking 2 at a time. So this is a square minus b square, so we can write this as a plus b into a minus b. So there will be a1 plus a2 into a1 minus a2, and this is a3 plus a4 into a3 minus a4. I will continue up to a2k minus 1 plus a2k into a2k minus 1 minus a2k. Now we know that in an AP, difference between any two successive terms, it is either D or minus D. Since it is A1 minus A2, so it will be this minus D. It will also be minus D. And in the same way, it is also minus D. So we'll take this minus D common, and then we'll have A1 plus A2 plus A3 plus A4 up to A2k, which is sum of first 2k terms of an AP. Now this is minus D, and this is n by 2. So it will be 2k by 2 and a plus l, which is a1 plus a2k. Now this 2 and 2 will cancel. So it is equal to minus d into k. This is a1 plus a2k. Now we also know that in an AP, this a2k will be equal to a1 plus 2k minus 1 into d. So we can write this d as a2k minus a1 upon 2k minus 1. So we'll put it here. So if we put it here, we'll get minus, and this is a2k minus a1 upon 2k minus 1 into k into a1 plus a2k. Now we'll take this minus sign here, then it will be a plus b into a minus b, which is k upon 2k minus 1 into a1 square minus a2k square, which is what we need to prove in this question. Now in this question it says, if the roots of the equation 10x cube minus cx square minus 54x minus 27 equals 0 are in HP, then find C and find all the roots. Now it is easier to work with an AP rather than an HP. So what we'll do is, we'll rather find an equation whose roots are reciprocal of roots of given equation. So for this, what we simply do is we'll replace x with 1 by x. So we can write 10 1 by x cube minus c 1 by x square minus 54 1 by x minus 27 equals 0. Now if we simplify and rearrange, we'll get this as 27x cube plus 54x square plus cx minus 10 equals 0. Now since its roots are reciprocal to the roots of given equation, roots of this equation, they are in AP, and let these roots be a minus d, a, and a plus d. Now we can write S1. S1 is sum of all the three roots, which in this case is 3a, and that will be equal to minus b upon a. So it will be minus 54 upon 27, which is minus 2. So value of a is minus 2 by 3. So we have this a as minus 2 by 3. Now since this a is root of this equation, it will satisfy this equation. So we'll put the value of x and find the value of c. So that will be 27, and this is minus 8 by 27 plus 54, and this is 4 by 9 minus 2c by 3 minus 10 equals 0. Now this is minus 8 plus 24 minus 2c by 3 minus 10 equals 0. Now this is 2c by 3 equals 6. Value of c is 9. So we get the value of c as 9. So in this question, value of c is 9. Now we need to find the other roots, and for it we need to find the value of d. So what we'll do is we'll write S3. Now S3 is alpha, beta, gamma. So it will be a into a square minus d square, and that will be equal to minus d upon a, which is 10 by 27. The value of a is minus 2 by 3. So that will be minus 2 by 3, and this is 4 by 9 minus d square, and this is 10 by 27. Now this is 5 and this is 9. So we can write minus 4 plus 9d square equals 5. So value of d is plus or minus 1. Now the roots are a minus d, and a plus d. So roots of this equation, they will be a minus d. So there will be minus 2 by 3 minus 1. So there will be minus 5 by 3, and then a, and then a plus d, which is 1 by 3. But these are roots of the equation whose roots are reciprocal to the roots of given equation. So we need to find roots of the given equation. So roots of given equation, they will be reciprocal to these roots. So they will be minus 3 by 5, minus 3 by 2, and 3, and the value of c we'll have here is 9. And that is the answer to this question. Now here the question is, if the sum of m terms of an AP is equal to sum of either the next n terms or the next p terms, then prove that 1 upon m plus n into 1 upon m minus 1 upon p will be equal to m plus p into 1 upon m minus 1 upon n, where n is unequal to p. So what we are given is sum of m terms is equal to sum of next n terms. Now we can write sum of next n terms as sum of m plus n minus sum of n terms. So it will give us the sum of next n terms. So we can write 2sm will be equal to s m plus n. And we are given that it is also equal to sum of next p terms. So another condition which we have here is 2sm will be equal to s m plus p, where n is unequal to p. Now we'll simplify this first condition. So we can write 2, and this is m by 2, 2a plus m minus 1 into d, and it will be equal to m plus n by 2 2a plus m plus n minus 1 into d. Now this 2 and 2 will cancel. Now what we'll also do is we let this 2a plus m minus 1 d as sum x. So we can write 2mx will be equal to m plus n, and here will be this 2a plus m minus 1 d is x plus n into d. Now we'll take this x on the left hand side. We can write m minus n into x, and that will be equal to m plus n into nd, or we can simply write x upon d will be equal to n into m plus n upon m minus n. Now similarly we can write it for this equation, and from here we'll get this x upon d as p into m plus p upon m minus p. Now we equate these two, we'll get n into m plus n upon m minus n, and that will be equal to p into m plus p upon m minus p. Now we can rearrange this as m plus n into m minus p into n, and that will be equal to p into m plus p into m minus n. Now we'll divide everything with m and p, and we'll divide it with these two terms. So we'll write m plus n. Now this n will cancel, and will be 1 upon p minus 1 upon m, and here will be this m plus p, and it will be 1 upon n minus 1 upon n, which is what we need to prove in this question. Now the question is, computer solved several problems in succession. The time it took the computer to solve each successive problem was same number of times smaller than the time it took to solve the preceding problem. How many problems were suggested to the computer if it spent 63.5 minutes to solve all the problems except for the first, and 127 minutes to solve all the problems except the last one, and 31.5 minutes to solve all the problems except the first two? Now let the time taken for the first problem be a, for the second it is AR, then it is AR square, AR cube, and we'll go all the way up to A r to the power n minus 2 and A r to the power n minus 1. So in total we'll have n problems. Now it says it spent 63.5 minutes to solve all the problems except for first. So for all these problems it has taken the time 63.5, 127 minutes to solve all the problems except the last one. So for all the problems except the last one, it has taken 127 minutes and 31.5 minutes to solve all the problems except for first two. So except for first two, time taken is 31.5 minutes. Now if we write this sum from A to A r to the power n minus 2, this sum will be A 1 minus r to the power n minus 1 upon 1 minus r. It is 127, and this sum from AR to AR to the power n minus 1, there will be AR 1 minus r to the power n minus 1 upon 1 minus r, and it will be 63.5. If we divide first with second, everything will cancel. We'll get this as 1 upon r, and that will be equal to 127 upon 63.5, which is 2. So value of r is 1 by 2. Now we know that time taken to solve problems from 2 to last, it is 63.5, and time taken to solve problems from 3 to last is 31.5. That means time taken to solve the second problem, it is AR, and it is equal to 63.5 minus 31.5. So it will be 63.5 minus 31.5, and that is 32. Now if we put r as 1 by 2, we'll get value of a as 64. So value of a is 64. So we have a and r. We need to find the value of n. So we put the value of a and r in this equation. So now we can write 64 1 minus 1 upon 2 to the power n minus 1 upon 1 minus 1 by 2, and that will be equal to 127. So this is 128. So we can write 1 minus 1 upon 2 to the power n minus 1 will be equal to 127 upon 128, or 1 upon 2 to the power n minus 1 is 1 upon 128. Now this is 1 upon 2 to the power 7. So n minus 1 equals 2 to the power 7. So value of n is 8. So in total, 8 problems were given to the computer, and that is the answer to this question. Now the question is, a GP and HP have same pth, qth and rth term ABC, show that a into b minus c log a plus b into c minus a log b plus c into a minus b log c, it is equal to 0. Now it says ABC are pth, qth and rth term of an HP. So that means 1 upon a, 1 upon b and 1 upon c are pth, qth and rth term for an AP. Now we can write this as a plus p minus 1b, it is equal to 1 by a plus q minus 1b, it is 1 by b, and a plus r minus 1 into d is 1 by c. Now if we subtract these two, we can write p minus q into d, it is equal to 1 upon a minus 1 upon b, and the same way if we subtract these two, we can write q minus rd equals 1 upon b minus 1 upon c. Now we are also given that ABC are pth, qth and rth term for a GP. So we can write this a as sum a dash r to the power p minus 1, b as sum a dash r to the power q minus 1, and c as sum a dash r to the power r minus 1. And if we take log, we can write log a equals log a dash plus p minus 1 log r log b, and this log a dash plus q minus 1 into log r, and log c equals log a dash plus r minus 1 into log r. So we will take everything as log. Now if we subtract these two, we can write log a minus log b, it is equal to p minus q into log r, and from second and third we can write log b minus log c as q minus r into log r. Now we'll come back to this first one. If we divide these two, we can write p minus q upon q minus r, it will be equal to b minus a upon ab into c minus b to bc, which is b minus ac upon a into c minus b. And if we divide these two, we can write log a minus log b upon log b minus log c will be equal to p minus q upon q minus r. Now if we equate these two, we can write c into b minus a upon a into c minus b will be equal to log a minus log b upon log b minus log c. Now we cross multiply, we can write c b minus a log b minus c b minus a log c will be equal to a c minus b log a minus a c minus b log b. Now we'll take everything on the left hand side. Then we can write this as a b minus c log a, now plus, and we'll take log b on the left hand side. It will be bc minus ac and ac minus ab. So there will be b c minus a log b, and this is plus. We'll take this plus sign, so it will be c into a minus b log c equals 0, which is what we need to prove in this question. Now here it says, let S and be sum of n terms of a GP whose first term and common ratios are a and r. Then prove that S1 plus S3 plus S5 up to S2n minus 1 is a n upon 1 minus r minus ar 1 minus r to the power 2n upon 1 minus r square into 1 plus r. Now we know that Sn is a into 1 minus r to the power n upon 1 minus r. Now we need to find the value of S1 plus S3 plus S5 up to S2n minus 1. Now S1 is a 1 minus r upon 1 minus r. S3 is a into 1 minus r cube upon 1 minus r. S5 is a 1 minus r to the power 5 upon 1 minus r, and S2n minus 1 will be a 1 minus r to the power 2n minus 1 upon 1 minus r. Now we'll add all these a1 minus r terms from all the expressions. Now number of terms in this series is n. So it will be an upon 1 minus r, and then we are left with this minus. We'll take ar upon 1 minus r common, and then we'll have 1 plus r square plus r to the power 4 up to r to the power 2n minus 2, which is nothing but a GP. So we can write this as an upon 1 minus r minus ar upon 1 minus r, and this is a 1 minus r square to the power n upon 1 minus r square. Now this is an upon 1 minus r, and this is minus ar upon 1 minus r, and this is 1 minus r to the power 2n, and this is a plus b into a minus b. So it will be 1 minus r into 1 plus r. So this sum, it will be an upon 1 minus r minus ar into 1 minus r to the power 2n upon 1 minus r square into 1 plus r, which is what we need to prove in this question. Now the question is, let there be m APs beginning with unity. So for each of the APs, first term is 1, and their common differences are 1, 2, 3 up to m. So their common differences are I. Show that sum of their nth term is m by 2 into mn minus m plus n plus 1. So if we write nth term for this ith series, it will be ai plus n minus 1 into I. So it will be 1 plus n minus 1 into I. Now we need to find sum of all these terms where I varies from 1 to n. Now it will be this summation. I varies from 1 to n, 1 plus n minus 1 into I. Now summation 1 is m, and this is n minus 1, and summation I is m into m plus 1 by 2. Now what we'll do is, we'll take m by 2 common. So if we take m by 2 common, we'll get this as 2 plus n minus 1 into m plus 1, and this is m by 2, and here will be this mn plus n minus m plus 1, which is what we need to prove in this question. Now here the question is, the sum of squares of three distinct real numbers which are in GP is s square and their sum is alpha s. Show that alpha s square belongs to 1 by 3 to 1 union 1 to 3. So we have three numbers in GP and let the numbers be A, AR and AR square. So we are given A plus AR square, and this is equal to alpha s and sum of their squares A square into 1 plus R square plus R to the power 4, and this is equal to S square. Now what we'll do is we'll add R square and we'll subtract R square. So we can write this as A square, and here it will be 1 plus R square whole square minus R square, and this is equal to S square. Now this is A plus B into A minus B, so we can write this as A 1 plus R square into A 1 minus R plus R square, and this is equal to S square. Now we know that A 1 plus R square, it is nothing but it is alpha s. So we'll replace it with alpha s. S will cancel once, so we can write A 1 minus R plus R square, and that will be equal to S upon alpha. So this is our first, this is second, and this is our third result. Now what we'll do is we'll divide first with third, then we can write 1 plus R square upon 1 minus R plus R square, and that will be equal to alpha square. Now we need to find a range of alpha square. Now we can write this as alpha square minus 1 into R square minus, and then it will be alpha square plus 1 into R plus alpha square minus 1 equals 0. Now we need a real value of R. So for this, D should be greater than 0. We are not considering D equals 0, because if D is equal to 0, then both the roots, they'll be equal. R1 equals R2, and we know that product of root is plus 1. So that means R1 and R2 will take the value either plus 1 or minus 1, in which case numbers won't be distinct. So we are discarding this case. So if we take D greater than 0, we'll get alpha square plus 1 whole square minus 4 alpha square minus 1 whole square, and it should be greater than 0. Now we'll write A plus B into A minus B. So it will be this 3 alpha square minus 1 into 3 minus alpha square. It should be greater than 0. Now if we write for alpha square, this is 1 by 3, this is 3, this is minus, plus and minus. What we need is plus. So value of alpha square should lie between 1 by 3 and 3. Now we also know that R cannot be 0, because again if R is 0, then we'll get two terms as 0, in which case we'll get alpha square equals 1. So R cannot be 0, that means value of alpha square, it cannot be 1. So from this we'll remove one value, which is 1. So answer to this question is alpha square should lie between 1 by 3 to 1 union 1 to 3, and that is the answer to this question. Now the question is, a series of natural numbers is divided into groups. In the first group we have 1, in the second group we have 2, 3, 4, in the third group we have 5, 6, 7, 8 and 9, and so on. We need to find some of the numbers in the nth group. So we are talking about nth group. Now in first group we have 1 number, in second group we have 3 numbers, in third group we have 5 numbers. So in nth group, we'll have A plus n minus 1 into D, that is 2n minus 1 numbers. So we'll have 2n minus 1 numbers. Now we know that in each group numbers are in AP whose common difference is 1. So we have common difference of 1. We need to find this first term. Now there are many ways to find this first term. Now what we can see is, here this is 1, for the second one it is 2, for this third one it is 9. So this is 1 square, this is 2 square, for the third it is 3 square, for this n minus 1th group last number will be n minus 1 square. So here this first term, it will be n minus 1 plus 1th term. So for this nth group, A is n minus 1 square plus 1. Common difference is 1. And number of terms, it is 2n minus 1. We just need to find its sum. So sum of these numbers will be n by 2. So it will be 2n minus 1 by 2. And then A plus L. So it will be this n minus 1 square plus 1 plus, and we know that here last term will be n square. So it will be simply n square. So we can write this as 2n minus 1 by 2, and here will be 2n square minus 2n plus 2, which will cancel. So it will be this 2n minus 1 into n square minus n plus 1. Now we have to express it in the form n minus 1 cube plus n cube. So what we'll do is we'll write this as n plus n minus 1, and here we'll subtract n and add n. So there will be n minus 1 whole square plus n. Now we multiply them, we can write n into n minus 1 square plus n square plus n minus 1 cube plus n into n minus 1. So it will be this n cube plus n minus 2n square plus n square plus n minus 1 cube plus n square minus n. Now this n square and 2n square will cancel, n and n will also cancel. So it will be this n minus 1 cube plus n cube, and that is what we need to prove in this question. Now for this question, another way to find this first term is, now in this first group there is only one term. So this next term is this 1 plus 2. Now here we have 1 plus 3, 4 terms, and this is 4 plus 1, 5th term. Now here we have 1 plus 3 plus 5, 9, and here will be this 10. So this first term, it will be 1 plus 3 plus 5 up to now till n minus 1th group. So you'll have n minus 1 terms plus 1. Now we know that sum of first n odd natural numbers is n square. Here we have n minus 1 terms. So there will be n minus 1 whole square plus 1. So that is another way of finding this first term, which again is n minus 1 whole square plus 1. Now here the questions, we are given x, y and z. Now x is this GP 1 plus cos square phi plus cos to the power 4 pi up to infinite. So this is a upon 1 minus r, which is 1 upon sin square phi. Now this y is 1 plus sin square phi plus sin to the power 4 phi up to infinite, and this is 1 upon 1 minus sin square phi, which is 1 upon cos square phi, and z is 1 plus cos square phi into sin square phi plus cos to the power 4 phi into sin to the power 4 phi up to infinite, which again is an infinite GP, which is a upon 1 minus r. Now what we'll do is we'll put the value of cos square phi and sin square phi. So from here we can write sin square phi as 1 by x and cos square phi as 1 by y. So from here we can write this z, it is equal to 1 upon 1 minus 1 upon xy, or z is equal to xy upon xy minus 1. So from here we can write this xyz, it is equal to xy plus 1, which is what we need to prove in this first part. Now for the second part, we need to prove that xy equals x plus y. Now we know that sin square phi plus cos square phi is 1. So if we add them, we can write sin square theta plus cos square theta 1, and that will be equal to 1 by x plus 1 by y. That means x into y equals x plus y. So we'll replace this x into y here. So from here we'll get x, y, z equals x plus y plus z. Now here this first question is we need to find sum of this series, which is summation r varies from 1 to n, summation s varies from 1 to n, delta rs, and this is 2 to the power r into 3 to the power s, where delta rs is 0 if r is unequal to s, and this is 1 if r is equal to s. So though it's a double summation problem, the problem is very simple. So when r and s, they are different, this entire term will be 0. So we'll only have non-zero terms when r equals s. So that means this s, it will be, when r is 1 and s is 1, it will be 2 into 3. When r is 2, s is 2, there will be 2 square into 3 square, 2 cube into 3 cube, and continue up to 2 to the power n into 3 to the power n. It is nothing but just another way of writing a GP. So this is another notation in which we can write a GP. So this s is nothing but a GP, which is 6 square, 6 cube up to 6 to the power n, which is a r to the power n minus 1 upon r minus 1, and that is the answer to this question. Now for this second part, it says we need to find this triple sum. I varies from 1 to n, j varies from 1 to I, and k varies from 1 to j, and this is 1. Now first we'll solve this. Now this is 1 plus 1 plus 1 j times, so it will be this summation I varies from 1 to n, and this is summation j varies from 1 to I, and this is j. Now summation j is I into I plus 1 by 2, so we can write this as this summation I varies from 1 to n, I into I plus 1 by 2, or this is this summation I square plus summation I divided by 2. Now summation I square is n plus 1, 2n plus 1 by 6, and summation I is n into n plus 1 by 2. Now what we'll do is we'll take n plus 1 by 6 common. We can write this as n plus 1 by 12, and here we'll have 2n plus 1, and here will be simply 3. So this is n plus 1, and this is 2n plus 4, which is 2 into n plus 2 upon 12, which we can also write as n plus 1, n plus 2 divided by 6, and that is the answer to this question. Now here the question is we need to find sum of these 4 series. Now this first one is we are given this series, which is 1 into 4 into 7, 1 upon 4 into 7 into 10, 1 upon 7 into 10 into 13. We need to find its sum up to nth term and then up to infinity. Now first we will find nth term for this series. Now this is 1, 4, 7. It's an AP. So its nth term will be a plus n minus 1, and common difference is 3. So there will be 3n minus 2. So it will be this 1 upon 3n minus 2, 3n plus 1, and 3n plus 4. Now basically this question is method of difference. Now difference between 1 and 7 is 6, 4 and 10 is 6, 7 and 13 is 6, and 3n minus 2 and 3n plus 4 is 6. So what we'll do is we'll multiply and divide everything with 6. So we can write s as 1 by 6, and this is 6 upon 147, and this is 6 upon 4710 up to 6 upon 3n minus 2, 3n plus 1, 3n plus 4. Now this is 1 by 6. Now we'll write this 6 as 7 minus 1. So it will be this 7 minus 1, and this is 147. Here we'll write this as 10 minus 4. This is 4 into 7 into 10. Here it is 13 minus 7. This is 7 into 10 into 13. And here it is 3n plus 4 minus 3n minus 2. So it will be 3n plus 4 minus 3n minus 2 upon 3n minus 2, 3n plus 1, 3n plus 4. And what we'll do is we'll split these terms. So you can write this is 1 by 6. Now here 7 will cancel. So it is 1 4 minus 4 7. Now here 10 will cancel. It will be 4 into 7. And here 4 will cancel. 7 into 10. Here 13 will cancel. So this is 7 into 10 minus 10 into 13. And we'll continue. And here this 3n plus 4 will cancel. So it will be this 3n minus 2. 3n plus 1 minus, and here 3n minus 2 will cancel, so it will be 3n plus 1 and 3n plus 4. Now if we look at these terms, these successive terms, they'll cancel. Now here we have this first one, then what remains is this last term. So this sum, it will be 1 by 6 into 1 by 4 minus 1 upon 3n plus 1 into 3n plus 4. And that is the sum up to n terms. Now, if we find sum up to infinite, we simply need to take this limit n tends to infinite, Sn. Now, if we take this limit n tends to infinite, this entire expression will be simply 0. So, sum of this limit up to infinity is 1 by 24. So, that is the answer to this first part. Now, this second question is find the sum of the series up to n terms. So, this series S is summation R varies from 1 to n, R plus 1, R plus 2, R plus 3. Now, one way of solving this question is by taking this product and then we'll have R to the power 4 R cube, which is very lengthy way of solving this question. So, what we'll do is we'll write its rth term as R plus 1, R plus 2 and R plus 3. Now we'll try and use method of difference in this. So the term before this one, it will be R minus 1 and term after R plus 3 will be R plus 4 and the difference is 5. So what we'll do is we'll multiply and divide everything with 5. So we can write 1 by 5 and this is R plus 1, R plus 2, R plus 3 into 5. Now we want to write this as 1 by 5 and this is R plus 1, R plus 2, R plus 3 and we'll write this as R plus 4 minus R minus 1 and we'll split it in two parts. We can write 1 by 4 and this is R plus 1, R plus 2, R plus 3, R plus 4 and minus and this is R minus 1, R plus 1, R plus 2, R plus 3. So that's our rth term. Now we can write this first term as 1 by 5 and this is 1 into 2 into 3 into 4 into 5 minus and this is 0. We can write its second term as 1 by 5 and this is 2 into 3 into 4 into 5 into 6 minus and this is 1 into 2 into 3 into 4 into 5. Third term is 1 by 5 and this is 3, 4, 5, 6, 7 minus and this is 2, 3, 4, 5 and 6 and its nth term is 1 by 5 n plus 1, n plus 2, n plus 3, n plus 4 minus n minus 1 n plus 1, n plus 2, n plus 3. Now Sn is sum of these first n terms. So we'll add them. We can add this Sn as t1 plus t2 plus t3 up to tn. Now here these terms they'll cancel. Now here we have this left. So here what remains is this expression. So it'll get cancelled. So it'll be this 1 by 5 into n n plus 1, n plus 2, n plus 3 into n plus 4. And that is the answer to this question. And since Sn is proportional to n, S infinite will be infinite. So as n approaches infinite, this sum is going to diverge. Now this third one is this summation. R varies from 1 to n, 1 upon 4 r square minus 1. So it will be this summation. R varies from 1 to n, and this is 2r minus 1, and this is 2r plus 1. Now here difference is 2. So what we'll do is we'll multiply and divide everything with 2. So it will be this summation. R varies from 1 to n, and this is 2 upon 2, and this is 2r minus 1 and 2r plus 1. Now we can write this as this summation. We'll take 1 by 2 common, and here will be this r varies from 1 to n, and we can write this as 2r plus 1 minus 2r minus 1 divided by 2r minus 1 and 2r plus 1, which is 1 by 2, and then this summation r varies from 1 to n. Now here 2r plus 1 will cancel, so it will be this 1 upon 2r minus 1, and here 2r minus 1 will cancel, and this is 2r plus 1. So we can write this sum of n terms as 1 by 2. Now we put r as 1, it will be 1 upon 1 minus 1 by 3, r as 2, so it will be 1 by 3 minus 1 by 5, and we'll continue up to 1 upon 2n minus 1 minus 1 upon 2n plus 1. Now 1 by 3, 1 by 5 will cancel. So here we have this first term, so we'll have this last term. So this Sn, it will be 1 by 2, 1 minus 1 upon 2n plus 1, or this is n upon 2n plus 1. Now we find S infinite, it will be this limit n tends to infinite, n upon 2n plus 1, and since this is infinite limit, answer to this limit is coefficient of highest power of n in the numerator and in the denominator. So it will be this 1 and 2. So sum of the series up to infinity is 1 by 2. And then we have this fourth one, which is this series Sn. So this is 1 by 4, 1 into 3, and this is 4 into 6. This is 1 into 3 into 5, and this is 4 into 6 into 8, and it goes up to n terms. Now for nth term we'll have 1, 3, 5. So it is an AP. So its nth term will be a plus n minus 1 into d. So that will be 2n minus 1. And here this is 4, 6, 8, which again is an AP. So this is a plus n minus 1 into d, which is 2n plus 2. 4, 6, 8, and this is 1, 3, 5. What seems to be missing is 2. So what we'll do is we'll multiply and divide everything with 2. So we can write this Sn as 2 into, and this is 2 into 4, and this is 1 into 3, and this is 2 into 4 into 6. This is 1 into 3 into 5, and this is 2 into 4 into 6 into 8, and this is 1 into 3 into 5 up to 2n minus 1, and here it will be 2 into 4 into 6 up to 2n plus 2. Now, if we write its general term will be rth term, and will be this 2 into, and then 1, 3, 5 up to 2r minus 1, and in the denominator will be 2 into 4 into 6 up to 2r plus 2. Now, because we have to use method of difference, somehow we have to express it as sum a minus b. So we have to introduce a minus b into this. So what we'll do is we'll write this as 1 here, and we can write this 2, and this is 1 into 3 into 5 up to 2r minus 1, and we can write this as 2r plus 2 minus 2r plus 1 whole divided by 2 into 4 into 6 up to 2r, and this is 2r plus 2. Now what we'll do is we'll split it in two parts. Now we can write this as TR, and this is 2. Now for this first part, 2R plus 2 will cancel, so we get this as 1 into 3 into 5 up to 2R minus 1 upon 2 into 4 into 6 up to 2R, and then minus, here it is 1 into 3 into 5, and this is 2R plus 1 upon 2 into 4 into 6 up to 2R plus 2. So that's your TR. Now if we write T1 will be 2, and here it is 1 by 2 minus, and this is 1 into 3 and 2 into 4, because if we put R as 1, this is 2 and this is 4, and here it will go up to 3. Now if we put T as 2, so it will be this 2. Now this is 1, 3, and this is from 2 to 4 minus, and this is 1, 3, 5, 2, 4, 6, and it will continue like this, and this nth term will be 2, and this is 1, 3, 5, 2n minus 1 upon 2, 4, 6, 2n minus, and this is 1, 3, 5, 2n plus 1 upon 2, 4, 6, 2n plus 2. Now Sn is sum of all these n terms. So if we add them, we'll get Sn. Now here these successive terms, they'll cancel, and since we have this term here, what will remain is this last term, so it'll cancel. So it'll be this 2 into 1 by 2 minus 1 into 3 into 5 up to 2n plus 1 upon 2 into 4 into 6 up to 2n plus 2. And if we find its sum up to infinite, it will be this limit n tends to infinite Sn. Now it will be this 2 into 1 by 2 minus, now here number of terms is n, and here number of terms is n plus 1. So here in the denominator, power of n will be greater, so it will be simply 0. So answer to this series will be 1. And that is the answer to this question. Now here we are given 2 questions, and for these 2 questions we have to find their nth term and sum of n terms. Now this first question is, we have the series 1 plus 5 plus 13 plus 29 plus 61 up to n terms. Now here difference is 4, 8, 16, 32, which is a GP. So this difference, it is in GP with common ratio 2. So we have this common ratio of 2, and we know that if difference is in GP, then its general term, it is written as a plus b into r to the power n minus 1, and r in this case is 2. So it will be this a plus b into 2 to the power of n minus 1. Now here we have 2 unknowns a and b. We put n as 1, it will be this a plus b, and it will be 1. And if we put n as 2, it will be a plus 2b, and it is 5. Now we subtract, we'll get b as 4, and if b is 4, value of a is minus 3. So its general term will be minus 3 plus 4 into 2 to the power of n minus 1, or it is minus 3 plus 2 to the power of n plus 1. Now we need to find sum of n terms. Now this Sn will be simply this summation r varies from 1 to n tr, which is this summation r varies from 1 to n minus 3 plus 2 to the power of r plus 1. Now summation of minus 3 is simply minus 3n, and then we'll have this summation r varies from 1 to n 2 to the power of r plus 1, which is nothing but a GP. Now for this GP, this first term is when you put r as 1, which is 4, common ratio is 2 and number of terms is n. So we can write this as minus 3n, and this is 4 into 2 to the power n minus 1 upon 2 minus 1. So it will be this minus 3n plus 2 to the power of n plus 2 minus 4. And that's the answer to this first question. Now this second question is, we need to find sum of this series and its nth term, 6, 13, 22, 33. Now here difference is 7, 9, 11. Now difference of difference is constant. We know that its nth term, it will be an square plus bn plus c. Now we'll use the shortcut. This is 2a, this is 3a plus b, and this is a plus b plus c. Now clearly a is 1, and if we put a as 1, we'll get b as 4, and if we put a as 1 and b as 4, we'll get c as 1. So its general term or its nth term will be n square plus 4n plus 1. Now we need to find sum of n terms, and there will be this summation. R varies from 1 to n, tr. So it will be this summation. R varies from 1 to n, and there will be r square plus 4r plus 1. Now summation r square is n plus 1, 2n plus 1 by 6 plus, and this is 4 n plus 1 by 2, and then plus n. Now we'll simplify these two. What we'll do is we'll take n plus 1 by 6 common. So we'll have 2n plus 1 plus 12 plus n. So it'll be this n plus 1, 2n plus 13 upon 6 plus n, and that is the answer to this question. Now the next question is, we need to find the sum of the first n terms of the sequence Sn, which is 1 plus 2 into 1 plus 1 by n plus 3 into 1 plus 1 by n whole square, 4 into 1 plus 1 by n whole cube up to, and the nth term will be n into 1 plus 1 by n whole to the power n minus 1. Now it's an AGP, and for an AGP what we'll do is we'll write the series again, and we'll multiply the series with its common ratio, which is 1 plus 1 by n, and we'll displace this series by one term. So here it will be 1 into 1 plus 1 by n, 2 into 1 plus 1 by n square, and then in the end we'll have this n into 1 plus 1 by n whole to the power n. Now what we'll do is we'll subtract this second series from first, so we'll get minus 1 by n Sn, and here it will be 1 plus, and this is 1 plus 1 by n, this is 1 plus 1 by n whole square. I'll go all the way up to this term, which is 1 plus 1 by n whole to the power of n minus 1 minus n into 1 plus 1 by n whole to the power n. Now it is nothing but a GP with first term 1, common ratio 1 plus 1 by n, and number of terms n. So it will be this minus 1 by n Sn will be a, and then r to the power n, which is 1 plus 1 by n to the power n minus 1 upon r minus 1. So it will be 1 plus 1 by n minus 1 and minus n into 1 plus 1 by n whole to the power n. Now this 1 and 1 will cancel. So we'll get this as minus 1 by n Sn, and here it will be this n 1 plus 1 by n whole to the power n minus n, and then minus n into 1 plus 1 by n whole to the power n. Now it will cancel. Now we'll take this minus n on the right hand side. We'll get this Sn as n square. So sum of first n terms of this sequence is n square. Now here the question is given that a to the power x equals b to the power y equals c to the power z equals d to the power u, where a, b, c, d are in GP, then show that x, y, z, u are in HP. Now what we'll do is we'll take this as lambda. Then if we take log, we can write x log a equals y log b equals z log c equals u log d equals log lambda, or log a equals log lambda upon x, log b equals log lambda upon y, log c equals log lambda upon z, and log d equals log lambda upon u. Now in the question it says a, b, c, d, they are in GP. Now we know that if a, b, c are in GP, then log a, log b, log c, and log d, they are in AP. Now we'll put the value of log a, log b, log c, and log d. So there will be log lambda upon x, log lambda upon y, log lambda upon z, and log lambda upon u. It will also be an AP. Now we'll divide everything with log lambda, and we know that if we divide each term with a constant, then it will still remain an AP. So that means this 1 upon x, 1 upon y, 1 upon z, and 1 upon u will be an AP, and reciprocal of an AP is HP. So that means x, y, z, u, they are in HP, and which is what we need to prove in this question. Now the question is find three numbers a, b, c between 2 and 18. So we have to find these three numbers a, b, c lying between 2 and 18 such that their sum is 25. So that means a plus b plus c is 25, and then it says the numbers 2a and b are consecutive terms of an AP. So that means 2a equals 2 plus b, and then it says b, c, and 18 are consecutive terms of a GP. So that means c square equals 18b. Now what we'll do is we'll put the value of a in this equation, we'll multiply it with 2, so we'll get 2a plus 2b plus 2c equals 50, and 2a is b plus 2, so there will be 3b plus 2c equals 48, and we know that 18b is c square. So what we'll do is we'll multiply everything with 6, so it will be this 18b plus 12c, and this is equal to 48 into 6, which is 288. Now this 18b is c square, so we can write c square plus 12c minus 288 is equal to 0. Now 288 is 6 into 48, which is 6 into 8 into 6. So we can write this as c square plus 24c minus 12c minus 288 equals 0. So from here we get c plus 24 and c minus 12 equals 0. So the only positive value of c in this case is c equals 12, as a, b, c lie between 2 and 18. Now once c is 12, b is c square by 18. So there will be 12 into 12 divided by 18. Value of b is 8. And once we have b and c, b plus c is 20, then the value of a is 5. So we get a as 5, b as 8, and c as 12. Now here the question is, an AP and an HP have the same first term and the same last term and the same number of terms. Prove that product of rth term from the beginning in one series and the rth term from the end in the other is independent of r. So suppose we have an AP whose first term is a and whose last term is b, and suppose number of terms is n. Now we know that its common difference, it will be b minus a upon n minus 1, and its rth term from the beginning, it will be a plus r minus 1 into d, which is a plus r minus 1, b minus a upon n minus 1, or simply we can write a n minus 1 plus b minus a r minus 1 upon n minus 1. We can also write this as a n minus r plus b r minus 1 upon n minus 1. So this is rth term of an AP from the beginning. Now if we look at HP, it says it has same first and last term. So this is a and b again, and again number of terms is n. Now we solve HP by making it an AP. So this is 1 by a and this is 1 by b. Number of terms is still n. Now its common difference will be 1 upon b minus 1 upon a upon n minus 1, which is a minus b upon ab into n minus 1. Now in this we need to find rth term from the end, and we know that rth term from the end is equal to n minus r plus 1th term from the beginning. So it will be this 1 by a plus n minus r into d, which is a minus b upon ab n minus 1. Now since this is corresponding term of an AP, so term of HP, which is rth term from the end, will be reciprocal of this, and it will be this AB n minus 1, and here will be this B n minus 1 plus n minus r a minus b. Now we'll take terms of b together, so it will be ab n minus 1 upon, and here this b, it will be n minus 1 minus n plus r. So it will be this b r minus 1 and plus n minus r into a. Now it says we have to prove that product of these two terms, it is independent of r. Now we multiply them, we'll get tr and thr from end, it will be a n minus r plus b r minus 1 upon n minus 1 into, and this is ab n minus 1 upon b r minus 1 plus n minus r into a. Now this expression will cancel, n minus 1 will also cancel, so this product, it is equal to ab, which is independent of r, and which is what we need to prove in this question. Now in this first question, it says value of x plus yz is 15 if a, x, y, z and b are in AP. So it says value of x plus y plus z, it is 15 if a, x, y, z and b, they are in AP. Now we know that in an AP, arithmetic mean of terms equidistant from beginning and end, it is equal. That means a plus b by 2, it is equal to x plus z upon 2, and it is equal to y. So in this x plus z will be equal to a plus b, and this y is a plus b by 2, and this is equal to 15. So from here we can write value of a plus b is 10, and that's our first equation. Now in the second part, it says if 1 by x plus 1 by y plus 1 by z equals 5 by 3, and if a, x, y, z and b, they are in HP, find the value of a and b. Now if they are in HP, then 1 upon a, 1 upon x, 1 upon y, 1 upon z and 1 upon b, they are in AP. That means again arithmetic mean of terms equidistant from beginning and end will be same. So 1 upon a plus 1 upon b by 2 must be equal to 1 upon x plus 1 upon z by 2 and will be equal to 1 upon y. Now this is 1 upon a plus 1 upon b and this is 1 upon a plus 1 upon b whole divided by 2. So it will be this 3 by 2 times 1 upon a plus 1 upon b and that will be equal to 5 by 3. Now we can write this as 3 by 2 a plus b upon ab and this is equal to 5 by 3. Now we already know a plus b is 10. So if we put a plus b as 10, we can write this as 3 by 2. This is 10 upon AB and this is equal to 5 by 3. Now I'll cancel. We'll get value of A into B as 9. So A into B is 9 and A plus B is 10. Now two equations, two unknowns. Now you put the value of B, we can write A plus 9 upon A equals 10 or A square minus 10A plus 9 equals 0. We get A minus 1, A minus 9 equals 0. So either the value of A is 1 or value of A is 9. And if A is 1, value of B is 9. And if A is 9, value of B is 1. And this is the answer to this question. Now this B question is the value of XYZ. It is 15 by 2 if A, X, Y, Z and B, they are in AP and this X, Y, Z is 18 by 5 if A, X, Y, Z and B, they are in HP. We have to find the value of A and B, assuming them to be positive integers. Now we'll take this first case when A, X, Y, Z and B, they are in AP. Now common difference of this AP will be simply B minus A upon 4. So this X will be simply A plus D. So it will be this A plus B minus A by 4, which is 3A plus B by 4. Y is X plus D. So it will be 2A plus B by 4 and Z will be Y plus D, which is A plus 3B by 4. So if we multiply X, Y and Z, we'll get 3A plus B into 2 times A plus B into A plus 3B upon 64. It is equal to 15 by 2 and this divided by 32. Now it says if A, X, Y, Z and B, they are in HP, then X into Y into Z, it is 18 by 5. Now if A, X, Y, Z and B, they are in HP, then 1 upon A, 1 upon X, 1 upon Y and 1 upon Z. So it will be same as this first equation where A, X, Y, Z, B, they are in AP. The only difference is here A is 1 upon A, B is 1 upon B, X is 1 upon X, Y is 1 upon Y and Z is 1 upon Z. So here we'll get 1 upon X into 1 upon Y into 1 upon Z as this 3 upon A plus 1 upon B, 1 upon A plus 1 upon B and 1 upon A plus 3 upon B by 32, and it will be equal to 5 by 18. So we can write this as 3b plus a into a plus b into b plus 3a upon 32, and this is ab cube will be equal to 5 by 18. Now we know that this 3a plus b, a plus b, a plus 3b upon 32, it is equal to 15 by 2. So we'll replace this value here with 15 by 2. So we can write 15 by 2 ab cube will be equal to 5 by 18. Now this is 9, this is 3, so we'll get ab cube equals 27, or the value of ab is 3. Now it says a and b are positive integers. So if a and b are positive integers, the only solutions we'll get is either a is 1 and b is 3, or a is 3 and b is 1. Now the question is, if n is root of this equation and if n HMs are inserted between a and c, show that difference between the first and last mean is equal to AC into a minus c. And the question, it says n is root of the equation x square into 1 minus AC minus x a square plus c square minus 1 plus AC equals 0. So that means n is going to satisfy this equation. So we'll get n square into 1 minus AC minus n a square plus c square minus 1 plus AC equals 0. So that's our first equation. Now it says n HMs are inserted between a and c. So in between a and c, we have inserted n HMs, or we can say between 1 upon a and 1 upon c, we have inserted n AMs. Now this is suppose H1, H2 and Hn, and corresponding AP is A1, A2 and AN. Now for this corresponding AP, its common difference will be 1 upon C minus 1 upon A upon N plus 1. Now this A1, it will be 1 by A plus D, which is 1 by A plus 1 by C minus 1 by A upon N plus 1, which is N upon A plus 1 upon C upon N plus 1. So that's your A1, and AN will be 1 upon C minus D, and there will be 1 upon C, and then minus D will be minus 1 upon C minus 1 upon A upon N plus 1, and there will be N upon C plus 1 upon A upon N plus 1. Now their corresponding harmonic means will be H1, which is N plus 1 upon NC plus A into AC, and Hn will be N plus 1 AC upon NA plus C. Now it says we need to show that difference between first and last mean is equal to AC into A minus C. We need to find H1 minus Hn. So we can write H1 minus Hn is, now this N plus 1 AC will be common, and then we'll have 1 upon NC plus A minus 1 upon N A plus C. Now if we take LCM, we can write N plus 1 AC and here it will be NA plus C minus NC minus A upon, and this is N square AC plus N A square plus C square plus AC. Now we can write this as N plus 1 AC. Here we'll take terms of N together, so there will be N A minus C and plus C minus A, and it will be N square AC plus N A square plus C square. Now what we'll do is we'll take A minus C common, so we'll get N plus 1 AC into A minus C, and here will be this N minus 1 upon N square AC plus N A square plus C square plus AB. Now this is A plus B into A minus B, so we can write this as N square minus 1 AC into A minus C upon N square AC plus N A square plus C square plus AB. Now we need to prove that this value, it is equal to AC into A minus C, which simply means that value of this expression, it must be 1. And here there is this correction, it is AC, so it should be this AC, so it should be AC, it should also be AC, and this is also AC. Now we know that N is the root of this given equation, so we can write N square into 1 minus AC minus N A square plus C square, and then minus 1 plus AC equals 0. Now we'll take this N square and 1 here, and we'll take everything else on the right hand side. So we can write N square minus 1, and that will be equal to N square AC plus N A square plus C square plus AC, and if we divide it, we'll get this result N square minus 1 upon N square AC plus N A square plus C square plus AC equals 1, and if we put it here, we'll get this as simply AC into A minus C, which is what we need to prove in this question. Now here the question is, we are given two series and we have to find the sum of this third series, which is 1 plus 3AB plus 5AB square up to infinite. Now this X is 1 plus 3A plus 6A square plus 10A cube up to infinite. Now what we'll do is, we'll write this series again and we'll multiply every term with A, and we'll displace this term by 1. So we'll get this A, and this is 3A square. Next one will be 6A cube up to infinite, and we'll subtract second from first. We'll get 1 minus AX, and will be equal to 1 plus 2A plus 3A square plus 4A cube up to infinite. Now this is an AGP. Now we'll write the series again and again, multiplying it with A and displacing by one term. So we'll get A into 1 minus AX, and here will be this A, and this is 2A square plus 3A cube up to infinite. Now we subtract second from first, we'll get 1 minus A square into X, and here will be this 1 plus A square plus A cube up to infinite, which is an infinite GP, which is A upon 1 minus R. So from here we can write X as 1 upon 1 minus A cube, and from here we can write 1 minus A is X to the power minus 1 by 3, or A is 1 minus X to the power minus 1 by 3, and that's our first result. Now this second series is y equals 1 plus 4b plus 10b square plus 20b cube up to infinite. Now again, we'll multiply it with its common ratio b and displace it by 1. So we'll get by will be equal to b plus 4b square plus 10b cube up to infinite. So it will be this 1 minus by, and this is 1 plus 3b plus 6b square plus 10b cube up to infinite. Now this series, it is same as this first series, 1 plus 3a plus 6a square plus 10a cube, and we know that answer to this series is 1 upon 1 minus a cube. So answer to this series will be 1 upon 1 minus b cube, or y is simply 1 upon 1 minus b to the power 4. From here we can write b as 1 minus y to the power minus 1 by 4, and that's our second result. So we have the value of a and b. Now we have to find sum of this series, which is 1 plus 3ab plus 5ab square up to infinite in terms of x and y. So again we write the same series and multiply it with common difference ab and displacing it by 1. So it will be this ab, and this is 3ab square up to infinite. Now we subtract second from first, we'll get 1 minus ab into s, and there will be 1 plus 2ab plus 2ab whole square up to infinite, and this is nothing but an infinite GP. So we can write this as 1 minus ab into s, and this is 1 plus, and this is 2ab upon 1 minus ab, which is 1 plus ab upon 1 minus ab. We can write this as 1 plus ab upon 1 minus ab whole square, where a is 1 minus x to the power minus 1 by 3, and b is 1 minus y to the power minus 1 by 4. If we put the value of a and b, we'll get the value of s in terms of x and y, which is what we need to find in this question. Now here it says the real numbers x1, x2 and x3 satisfying the equation x cube minus x square plus beta x plus gamma equals 0. They are in AP. Then find the intervals in which beta and gamma lies. Now suppose these three roots x1, x2 and x3, which are in AP, they are a minus d, a, and a plus d. Now if we write s1, which is sum of roots, we can write 3a equals 1, or the value of a is 1 by 3. Now we write s2, which is sum of roots taken 2 at a time. So it will be this a into a minus d plus a into a plus d plus a minus d into a plus d, and that will be equal to beta. Now here ad will cancel, so we'll get this as 2 times a square plus a square minus d square. It is equal to beta, or we can write d square is 3a square minus beta. Now a is 1 by 3, so we'll get this as 1 by 3 minus beta. Now d square, it should be greater than or equal to 0. So from here we'll get this condition that value of beta must be less than or equal to 1 by 3. Now we need to find a range of gamma. Now for gamma, we write S3. Now S3 is product of roots. So this is a minus d into a plus d, and it will be equal to minus gamma. Now this is a into a square minus d square, and this is minus gamma. Now A is 1 by 3. So it will be this 1 by 3 and this is 1 by 9 minus d square and this is minus gamma. We can write d square as 1 by 9 plus 3 gamma. Now again d square, it should be greater than or equal to 0. So from here we'll get value of gamma, it should be greater than or equal to minus 1 by 27. So we have range of beta and we also have a range of gamma, and that is the answer to this question. Now the question is, for an odd integer n, we have to find the value of n cube minus n minus 1 cube and goes all the way up to minus 1 to the power n minus 1 into 1 cube, and suppose this sum is s. Now we know that this n is an odd integer, and if n is odd, then minus 1 to the power n minus 1 will be even, so it will be this plus 1. So we can also write this as 1 cube minus 2 cube plus 3 cube minus 4 cube. I'll go all the way up to minus n minus 1 cube plus n cube. Now what we'll do is we'll add 2 cube and we'll also subtract 2 cube. In the same way, we'll add 4 cube and we'll subtract 4 cube, and we'll do it for all the negative numbers, plus n minus 1 cube and then minus n minus 1 cube. And what we'll do is we'll take all these positive terms together. So this s will become 1 cube plus 2 cube plus 3 cube up to n cube, and we'll take all the negative terms together. So here we have minus 2 cube and minus 2 cube, so there will be minus 2 into 2 cube plus 4 cube up to n minus 1 cube. Now we can write this as 1 cube plus 2 cube up to n cube, and here we'll take 2 cube common, so there will be 16, and here we'll have 1 cube plus 2 cube up to n minus 1 by 2 whole cube. Now since n is odd, n minus 1 upon 2, it is an integer, so there is no problem using this value. Now this is 1 cube, 2 cube up to n cube, so it will be this n plus 1 by 2 whole square, and this is minus 16, and this is 1 cube, 2 cube up to n minus 1 by 2 whole cube, so there will be n into n plus 1 by 2 whole square. Now 2 square is 4, so this 4, 4, 16. 16 will cancel, and we can take n plus 1 upon 2 whole square common. So we'll take n plus 1 upon 2 whole square common, and what remains is this n square minus n minus 1 square. Now this is a plus b into a minus b, so it will be this 2n minus 1. So it will be this n plus 1 by 2 whole square into 2n minus 1, and that is the answer to this question. Now in the question it says, if a, b, c are first 3 terms of a geometric series. So we are given a geometric progression or geometric series which is a, b and c. Now rather than taking them as a, b and c, we'll take them as a, ar and ar square. Now it says harmonic mean of a and b is 12. So their harmonic mean is 12 and that of b and c is 36. Now harmonic mean of a and ar is 2 a into ar upon a 1 plus r, and they'll be equal to 12. Now here a, it will cancel, so we can write ar equals 6 times 1 plus r, and that's our first equation. And harmonic mean of ar and ar square will be 2 times ar into AR square upon AR plus AR square. So we'll take AR common and it will be this 1 plus R and there will be 36. Now this AR, it will cancel and we know that AR upon 1 plus R, it is 6. So we can write 2 times R into 6, it is equal to 36. So value of R is 3. And if we put R as 3, we get 3A and this is 6 into 4 or value of A is 8. So we have A and R. Now we need to write first 5 terms. So it will be 8, 24, 72, 216 and 648, and that is the answer to this question. Now here the question is, for an AP, mth term is 1 by n and nth term is 1 by n. We will find its mnth term. It's a very simple question. Now mth term is a plus m minus 1 into d and it is 1 by n, and nth term is a plus n minus 1 into d, it is 1 by m. Now we subtract second from first, we get m minus n into d will be equal to 1 by n minus 1 by m, which is m minus n upon mn. And since m and n, they are unequal, we'll get d as 1 by mn. Now if we put d as 1 by mn, we get a plus m minus 1 upon mn and it is equal to 1 by m. From here we get a also as 1 by mn. And once we have a and d, we can write its mnth term. Its mnth term will be a plus mn minus 1 into d. Now a is 1 by mn, so it will be this 1 by mn plus mn minus 1, and this d is also 1 by mn. So it will be this mn by mn, which is 1. So answer to this question is 1, which is your option C. Now here the question is, given a 3-digit number whose digits are 3 successive terms of a GP. Now suppose 3-digit number is XYZ, and here I am just writing their digits. So this is units digit, this is tens digit, and this is hundreds digit, and they are in GP. So that means we have y square equals xz, and that's our first equation. Now it says, if we subtract 792 from it, we'll get a number written by same digits in the reverse order. Now if we subtract 792 from it, we'll get the same number in reverse order. So there will be zyx. Now actual way of writing it will be, the number is 100x plus 10y plus z, and we are subtracting 700 plus 90 plus 2, and that will be equal to 100z plus 10y plus x. Now this 10y and 10y will cancel, so we can write 99x minus 99z, and that will be equal to 792, and this is 99x minus z, and we can write this as 11 into 72. Now this is 9 and this is 8. So the second equation we get is x minus z equals 8. Now it says, if we subtract 4 from 100th digit of the initial number and leave the other digits unchanged, we get a number whose digits are successive terms of an AP. So we subtract 4 from this 100th number, so x minus 4, y and z. Now it says they are in AP. So that means 2y equals x plus z minus 4. Now since we have 3 equations and 3 unknowns, we should be able to find the value of x, y and z. Now we need to find the value of x, y and z. So what we'll do is we'll write z as x minus 8, and if we put z as x minus 8 here, we'll get 2y equals 2x minus 12, or y equals x minus 6, and then we'll put the value of y and z in this equation. So we'll get x minus 6 whole square equals x into x minus 8, which is x square minus 12x plus 36, and that will be equal to x square minus 8x. Now this x square will cancel, so we'll get 4x equals 36. Value of x is 9. So we have our x and the value of x is 9. Now if we put x as 9, we'll get y as 9 minus 6. So y will be 3 and z is 9 minus 8. So z is 1. So this number will be 931. And that is the answer to this question. Now in this question, we need to find sum of the series up to n terms, and the series given is 1 upon x plus 1 plus 2x upon x plus 1, x plus 2, and this is 3x square upon x plus 1, x plus 2, x plus 3, and will continue up to n terms, and the nth term will be n x to the power n minus 1 upon x plus 1, x plus 2 up to x plus n. Now what we'll do is, for this second term, we'll add x square and subtract x square. Here we'll add x cube and subtract x cube, and here we'll add x to the power n and subtract x to the power n. So we can write 1 upon x plus 1, and here if we take x common, it will be x plus 2 minus x square upon x plus 1, x plus 2. Here it will be x square, x plus 3 minus x cube upon x plus 1, x plus 2, x plus 3. I'll continue up to x plus n, x to the power n minus 1 minus x to the power n upon x plus 1, x plus 2 up to x plus n. Now what we'll do is we'll split each term in two parts. So we can write 1 upon x plus 1, and here x plus 2 will cancel. It will be x upon x plus 1 and minus x square upon x plus 1, x plus 2. Here x plus 3 will cancel, so it will be x square upon x plus 1, x plus 2, and then all other terms. And here x plus n will cancel, so there will be x to the power n minus 1, x plus 1 up to x plus n minus 1 minus x to the power n upon x plus 1 up to x plus n. Now here all these terms, they'll cancel. So what we're left is with these terms and this term. Now 1 plus x upon 1 plus x is 1. So this s will be simply 1 minus x to the power n upon x plus 1, x plus 2 up to x plus n. So that is the sum up to n terms. Now the second question is, we are given this sum a1 upon 1 plus a1 plus a2 upon 1 plus a1 into 1 plus a2 plus a3 upon 1 plus a1, 1 plus a2, 1 plus a3, and it goes all the way up to an upon 1 plus a1 into 1 plus a2 up to 1 plus an. Now in this also we need to introduce a negative sign. So what we'll do is we'll add 1 and subtract 1. So we'll add 1 and subtract 1 in each of the terms except this first one, and then we'll split each term in two parts. So we can write this sum as a upon 1 plus a1. Now here a2 plus 1 will cancel, so it'll be 1 upon 1 plus a1, and then minus it'll be 1 upon 1 plus a1 into 1 plus a2. In the same way, a3 plus 1 will cancel, so it'll be 1 upon 1 plus a1, 1 plus a2, and then minus 1 upon 1 plus a1, 1 plus a2, and 1 plus a3. I'll continue, and in the end we'll have minus 1 upon 1 plus a1, 1 plus a2 up to 1 plus an. Now all these successive terms, they'll cancel. So what we'll get is these first two terms and this last term. Now a plus 1 upon 1 plus a1, this is a1. So it is 1. So this sum will be 1 minus 1 upon 1 plus a1 into 1 plus a2 up to 1 plus an. And that is the answer to this question. Now here the question is, if A, B and C, they are in GP and log A base C, log C base B and log B base A, they are in AP, then show that common difference of AP, it must be 3 by 2. Now what we'll actually do is, we'll take these three terms as B by R, Bn, Br, where R is common ratio of this GP. That's your A, this is your B, and that's your C. Now if we take log to the base B, we can write log A base B will be log B minus log R. So it will be 1 minus log R base B. And if we take log R base B as T, we can write log A base B as simply 1 minus T. Now we write log B base B. Log B base B obviously will be 1. And then we'll write log C base B. And log C base B will be log B into R, which is log B plus log R. So it will be 1 upon log R base B, and it will be simply 1 plus T, where we have taken T as log R to the base B. Now in the question it says log A to the base C, log C to the base B, and log B to the base A, they are in AP. Now we know that log A to the base C is log A upon log C to any base, and here we'll change the base to B. So we can simply write this as log A to the base B upon log C to the base B, and this is log C to the base B, and here it is log B to the base B, which is 1 upon, and this is log A to the base B, and they are in AP. Now log A is simply 1 minus T, and this is 1 plus T. This is 1 plus T, and here it is 1 upon 1 minus T, and it says it is an AP. Now since it is an AP, 2 times 1 plus T will be equal to 1 minus T upon 1 plus T plus 1 upon 1 minus T. So it will be this 2 into 1 plus T, and it is 1 minus T plus 1 plus T upon 1 plus T into 1 minus T, which is 1 minus T square. So we can write 2 into 1 plus T into 1 minus T square, and it will be equal to 1 plus T square minus 2T, and this is 1 plus T. So this is 2 plus 2T minus 2t square minus 2t cube, and that will be t square minus t plus 2. Now we can write this as 2t cube, and then we'll have 3t square and then we'll have minus 3t, and this 2 and 2 will cancel, so it will be equal to 0, or we can write 2t square plus 3t minus 3, it is equal to 0. So this is our first result. Now it says we have to find common difference of this AP. Now we know that its common difference, it will be this minus this, so it will be 1 upon 1 minus t minus 1 plus t, which is 1 minus t square upon 1 minus t. So its common difference is t square upon 1 minus t. Now if we rearrange this, we can write 2t square equals 3 into 1 minus t, or t square upon 1 minus t equals 3 by 2. So this value, it is equal to 3 by 2. So common difference of this AP, it will be simply 3 by 2, and that is the answer to this question. Now here the questions, we are given this relation which is an equals an minus 1 plus 1 upon an minus 1 for all n greater than 1, and it is given that a1, it is equal to 1. Now it says we need to show that A75 will lie between 12 and 15. Now A1 is 1. If we write A2 is 1 plus 1. So A2 will be 2. A3 will be 2 plus 1 upon 2, which is greater than 2. And since it is an increasing sequence, any an will be greater than 2 for all n greater than 2. Now we look at this given condition. Now it says an equals an minus 1 plus 1 upon an minus 1. Now we square it, we can write an square as an minus 1 square plus 1 upon an minus 1 square plus 2. Now we know that this is always greater than an minus 1 square plus 2, because we are leaving out this positive term 1 upon an minus 1 square, and we know that any an, it is greater than 2, then 1 upon an will be less than 1 by 2, or 1 upon an square will be less than 1 by 4. That means it will always be less than 1. So we can write it will be less than an minus 1 square plus 3. So from here we can write an minus 1 square plus 2 will be less than an square, and will be less than an minus 1 square plus 3. Now we can also write this as 2 is less than an square minus an minus 1 square, and will be less than 3. So we have this relationship that difference of squares of any two successive terms of the sequence will lie between 2 and 3. Now we'll start with n as 2. So we can write 2 is less than a2 square minus a1 square, and will be less than 3. And if we put n as 3, we'll write a3 square minus a2 square will be less than 3. And for n equals 4, we'll get a4 square minus a3 square will be less than 3. And we'll continue up to an square minus an minus square will be less than 3. Now if we add them all up, here this a2 square will cancel, a3 square will cancel. So all these terms will cancel. We can write 2 plus 2 plus 2 n minus 1 times. So there will be 2 n minus 1 will be less than an square minus a1 square, and will be less than 3 plus 3 plus 3 n minus 1 times, and there will be 3 n minus 1. Now we are given that value of a1 is 1. So we can write 2n minus 1 plus 1 will be less than an square and will be less than 3n minus 1 plus 1. So this is the result that we have from the given condition. Now it says we need to prove that A75 will lie between 12 and 15. So what we'll do is we'll put the value of n as 75. So we'll put n equals 75. So this is 2 and this is 74 plus 1 will be less than A75 square and will be less than 3 into 74 plus 1. Now this is 149. It is less than A75 square and will be less than 223. Now we know that 149 is greater than 144 and 223 is less than 225. We can write 12 square is less than A75 square and will be less than 15 square, or A75 will lie between 12 and 15, and that is the answer to this question. Now this question, it says in a GP ratio of sum of first 11 terms to the sum of last 11 terms is 1 by 8. So we have this GP which is AR square, and it goes all the way up to AR to the power n minus 1. Now sum of first 11 terms will be given by A 1 minus r to the power 11 upon 1 minus r. So this is sum of first 11 to the sum of last 11. So we need to find sum of last 11. Now if you look at last 11, this last 11 terms will be a GP from this side, and here this first term will be AR to the power n minus 1 and its common ratio will be 1 by n. So we can write this as A r to the power n minus 1 upon r to the power 11 minus 1 upon 1 upon r minus 1, which will be A r to the power, now this is n minus 1 and this is r to the power 10, so it will be A r to the power n minus 11 into 1 minus r to the power 11 upon 1 minus r. Now if we take their ratio, it is given that its ratio is 1 by 8. So S first 11 upon S last 11 will be A 1 minus r to the power 11 upon 1 minus r into 1 minus r upon A r to the power 9 minus 11 into 1 minus r to the power 11. Now it will cancel. 1 minus r will also cancel. So it is 1 upon r to the power n minus 11, and it is given as 1 by 8. So the condition that we have here is r to the power n minus 11, it is equal to 8. And that's our first condition. And it says the ratio of sum of all the terms without the first 9 to the sum of all the terms without the last 9 is 2. Find number of terms in this GP. Now if we leave out first 9 terms, then we'll start with 10th term, which is A r to the power n. I'll go all the way up to A r to the power n minus 1, and here number of terms will be n minus 9. So sum of such numbers will be A r to the power 9 1 minus r to the power n minus 9 upon 1 minus r, and then this sum where we have not considered last 9 numbers. So this series will start from AR, and then it will contain n minus 9 terms. So here will be this A 1 minus r to the power n minus 9 upon 1 minus r. Now it says this ratio is equal to 2. Now if we divide them, we can write A r to the power 9 1 minus r to the power n minus 9 upon 1 minus r into 1 minus r upon A 1 minus r to the power n minus 9, and this is equal to 2. Now all of this they'll cancel, we'll get r to the power 9 as 2. So this 2 is simply r to the power 9. So what we'll do is we'll put it here. So we can write r to the power n minus 11. It is equal to 2 cube, which is r to the power 27. So value of n is nothing but 38. So answer to this question is value of n is 38. Now the question is, let p and q be the roots of equation x square minus 2x plus a. So we have this equation x square minus 2x plus a equals 0, and here roots are p and q, and r and s are the roots of the equation x square minus 18x plus b equals 0, and here roots are r and s. Now it says p is less than q, and it is less than r, and it is less than s, and they are in AP. We need to find the value of capital A and capital B. Now suppose the roots are p plus d, p plus 2d, and p plus 3d, where d is greater than 0, as it is an increasing AP. Now for this first equation, we can write sum of roots. So we can write 2p plus d, it is equal to 2, and product of roots, so there will be p into p plus d will be equal to a. And for the second equation, again we can write sum of roots, so it will be this 2p plus 5d will be equal to 18, and product of roots p plus 2d into p plus 3d, that will be b. Now from these two equations we can find the value of p and d. Now if we subtract first from second, we can write 4d equals 16. That means value of d is 4, and if we put d as 4, we'll get value of p as minus 1. So we have p as minus 1 and d as 4. Now the four terms of AP are minus 1 plus 4, 3, 3 plus 4, 7, 7 plus 4, 11. Now A is nothing but product of roots. So this is minus 3, and B is product of roots of this equation, and that will be 77. So value of A is minus 3 and value of B is 77, and that is the answer to this question. Now it says, if there are n quantities in GP with common ratios R. So we have this GP, who's suppose A, AR, AR square, and A R to the power n minus 1. And if SM denotes the sum of first m terms, so this SM, it is A plus AR plus AR square up to AR to the power m minus 1. Then it says that show that the sum of product of these m terms taken 2 at a time is this value. Now we know that this SM, it is A 1 minus r to the power m upon 1 minus r. Now if we square both sides, we can write A plus AR plus AR square up to AR to the power m minus 1 whole square, and it is equal to A square, and then 1 minus r to the power m square upon 1 minus r whole square. Now we can write this as a square plus ar whole square, ar square whole square plus ar to the power m minus 1 square plus 2 times, there will be AB, AC, AD, BC, CD. That is, it will be sum of product of these m terms taken 2 at a time, which is what we need to find in this question. Let us say this is a required sum S, and this is equal to a square into 1 minus r to the power m whole square upon 1 minus r square. Now this again, it is a GP whose first term is a square and common ratio is r square and number of terms is m. So it will be this a square 1 minus r square to the power m upon 1 minus r square plus 2s, and that will be equal to a square 1 minus r to the power m whole square upon 1 minus r square. Now we will take this on right hand side. We can write 2s equals a square 1 minus r to the power m whole square upon 1 minus r square minus, and this is a square, and we can write this as a plus b into a minus b. So we'll write 1 plus r to the power m into 1 minus r to the power m upon, and this is also a plus b into a minus b. So it will be this 1 plus r into 1 minus r. Now what we'll do is we'll take a square 1 minus r to the power m upon 1 minus r common. So we can write 2s equals a square 1 minus r to the power m upon 1 minus r, and then what you're left with is 1 minus r to the power m upon 1 minus r minus 1 plus r to the power m upon 1 plus r. Now this a into 1 minus r to the power m upon 1 minus r, it is nothing but sum of m terms, which is Sm. So we can write 2s will be equal to a into Sm, and here we can write this as 1 minus r into 1 plus r, and here will be this 1 plus r minus r to the power m minus r to the power m plus 1, and here will be this minus 1 minus r to the power m plus r to the power m plus 1. Now here this 1 will cancel and r to the power m plus 1 will also cancel. So we can write this as 2s equals a sm, and here we'll take 2 common and we'll also take r common, and there will be 1 minus r to the power m minus 1 upon 1 plus r into 1 minus r. Now this a 1 minus r to the power m minus 1 upon 1 minus r, it is nothing but it is s m minus 1, and this 2 and 2 will cancel. So we'll get this s as sm into this sm minus 1, and then we also have this r upon 1 plus r, which is what we need to prove in this question. Now the sixth question is, we are given the sequence of real numbers defined as u1, it is 1, and un plus 1, it is un plus 1 upon un for all n greater than or equal to 1. Now if we find u2 is going to be 1 plus 1, it will be this 2. u3 it will be 2 plus 1 by 2, 2.5. So any ui, it will always be greater than or equal to 2 when I is greater than or equal to 2. Because we are adding something to un and it is clearly an increasing function. Now what you're going to do is, we're going to write this as un plus 1 square will be un square plus 1 upon un square plus 2, or un plus 1 square minus un square will be equal to 2 plus 1 upon un square. And this is the iterative relation we are going to use for our telescopic summation. Since we need un, we are not going to start with n plus 1, we are going to start with un. So we can write un square minus un minus 1 square will be 2 plus 1 upon un minus 1 square. Next one will be un minus 1 square minus un minus 2 square, and that will be 2 plus 1 upon un minus 2 square, and will continue up to u2 square minus u1 square, and that will be 2 plus 1 upon u1 square. Now if we add all of them, then these successive terms, they'll cancel. So we can write un square minus u1 square, and here this is 2 plus 2 plus 2, and it is from 1 to n minus 1 times. So there will be 2 n minus 1, and plus this is 1 upon u1 square plus 1 upon u2 square up to 1 upon un minus 1 square. Now u1 is 1, so this is 1, so we can write un square minus 1, and here will be this 2n minus 2 plus, now this u1 square again will be this 1, and this u2 square, u3 square, and un minus 1 square, we know that any ui is greater than 2 when I is greater than or equal to 2. So 1 upon ui will be less than or equal to 1 upon 2, or 1 upon ui square will be less than or equal to 1 by 4 for any I greater than or equal to 2. So for all these terms from 2 to n minus 1, we can write this summation I varies from 2 to n minus 1, 1 upon ui square, it will be less than or equal to, now this is 2n minus 2 plus 1, and plus, now this is 1 by 4, 1 by 4, 1 by 4, n minus 2 times. So it will be this n minus 2 by 4. So we'll take this one on the right hand side. So this 1, 1 and 2 will cancel. So we can write un square will be less than or equal to, now this is 2n plus n minus 2 by 4, or we can write un square is less than, now this is 9n minus 2 by 4, now this 9n minus 2 by 4 will be less than 9n by 4. If we take square root both sides, we can write this un, it will be less than 3 by 2 under root n, and which is what we need to prove in this question.